Here we go. Hey everyone, week 8 office hours. Is it week 8?
Yeah.
Yeah. Somehow.
So we've got a couple questions. We've got some questions from quiz 5, the quiz that was just last week. Then we've got some just general questions about balancing and ionic equations. So we're going to start with quiz 5. The isomers question. So it was a C5H8O2. And so there's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Quick trick I want to show you all. When you have a hydrocarbon, there's a trick to figure out how many double bonds you need to have. And that's called saturation. Or they call it degrees of unsaturation. How many of you are going to take OChem in the future? You'll need this. If you're not taking OChem, don't worry about it. But this is going to be a nice trick. It's not going to come up. There's not much time left in the quarter. But essentially, it's the number of carbons times 2 plus 2. And so what's going on here is you can imagine if you had 5 carbons, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and then 11, 12 because you've got your atoms. So you take your number of carbons, you multiply by 2 and add 2. That would be a completely saturated carbon chain. You've got as many hydrogens as possible. If you had a C5H10, that would be 1 degree of unsaturation, so you'd need 1 double bond. If you had a C5H8, that's 2 degrees of unsaturation, so you need 2 double bonds, or a triple bond, or a double bond in a ring, but you need some combination of things that make it so this happens. So to make it a ketone, we need a double bonded carbon, oxygen someplace in the middle. I'm going to put it directly in the middle. 1, 2, 3, 4, 5. I'm going to put it directly in the middle, so there's no doubt about it, but you could pick either of these other carbons as well. And then I'm going to put a double bond, and I'm going to put an alcohol over here. Right? I'm going to double check my formula. So this looks like a C5H8O. I've got my 2 degrees of unsaturation, so it's going to be, I think it should be C5H8. I've got 2 oxygens, so it should be 2 O's. I'm going to count my hydrogens still. 1, 2, 3, 4, 5, 6, 7, 8. So that should be C5H8O. As long as that alcohol functional group is not directly next to the oxygen double bond, it's not coming off the same carbon, it's 2 different functional groups in the same structure. And this should work if the double bond O was here. If it was there, it would be a carboxylic acid. But if it was here, it should work. This double bond could move around. There should be several different possible isomers. I did notice something's not working in LabPal in the way I intended, so I'll have to look into that. And I thought it was going to be a quick fix, but it's more I can't figure out what's going wrong. So I'm going to have to dig into the code a bit and figure out what's going wrong. So that's particularly the ketone one looks like it's not behaving correctly. So that might mean like a third of the students missed a point when they should have gotten a point, and I'll have to look into that. The other one we wanted to do was look at number 3, the electronegativity question. Oh, sorry, if we're ready to move on. That one, it seems like everyone got that one, and it's just the coding issue. So we'll move on to number 3, which is looking at electronegativity. Which atoms did you have?
So I had to select the most electronegative, and I had Cl, N, S, and C. And I was torn between N and S because they're both the same distance away from oxygen.
Yeah.
I was like, I think I'm going to select the higher one because I know...
Wait, so it was saying select the lowest?
The most electronegative.
Oh, most electronegative. So there's going to be something better than N and S in that case. What's more electronegative than oxygen? There's only one thing more electronegative than oxygen.
Fluorine.
Fluorine. So it's going to be the thing that's closest to fluorine. Right? And it turns out that chlorine in this case is going to be the most electronegative. Right? So, and I know the way I say this in class might be a little ambiguous because I always say oxygen is the most electronegative besides fluorine. Right? Fluorine is more electronegative. It's just we don't see it happen very much in nature. We don't see it in many of the organic compounds we're looking at. So we don't really care much about how electronegative fluorine is. It's usually oxygen's electronegativity that's more interesting. So that was just like a little detail. It's important to keep track of those little details, because I know you're like really close to getting all of this stuff, and it's always like little details
it's
here
just
and
like I
there.
had oxygen in my head. I'm like, all right,
Yeah.
which one's closest to oxygen?
Right. And so it's, yeah, and then fluorine is more. And so that's the place where it's just like it's that top right corner. The thing that I thought you were going to get tripped up on, which is why I really wanted to do this one, is sometimes you'll see a list like this, and it will include neon. And people just blindly apply, like, oh, it's the top right corner. Neon's further top to the right, so neon is most electronegative. It's like, no, noble gases are not. Noble gases have no electron affinity, and they have no electronegativity. I mean, they do, but they're really weird, right? They don't want electrons. You have to force electrons onto them. So things with that full shell, they're not going to behave. So I thought that was the thing that was going to trick you. But you,
I had oxygen.
yeah, and it's that. This is the place where memorizing things, which worked really well for us in high school, doesn't work as well in college. Right? There needs to be that deeper kind of like understanding of like, well, why is it oxygen?
Yeah.
And it's that extra step that becomes really important. Those were the two specific questions we had. We also had general kind of what's happening with balancing and net ionic equations. Did you have a specific question?
No, I just had another topic maybe.
Sure, we can add another topic on here.
I just know that we should mark up our periodic tables well, just for note purposes, and I wanted to know if we can go through like the best things to put on a periodic table. So like trends, of course, but maybe other information besides the trends that might be useful.
It's difficult for me to say because that's been like several weeks of information.
Yeah, totally.
So it would take a lot to go over that and explain why we're doing it. Because like just doing the marks by themselves is not that great.
Yeah.
It's understanding the marks that becomes more important. Like, why are you doing it? So we can talk about
I
that
was
for
gonna say we
sure.
can single out maybe the most important topics, but if not, that's totally fine.
We can talk about some of that for sure. But there's like it's a long conversation. But we can see what we get to. Yeah.
A question would be, what does polarizability mean?
Okay, polarizability. That's kind of another.
Yeah.
Give me 1 second. Hey, did you have a specific question?
I have questions about redox, but it didn't look like anyone was going to ask them.
Well, then you can ask.
But I don't know how much time.
We can throw. Well, we're about to talk about.
You can go
balancing
first.
reactions and stuff. Yeah. You don't have much time. You have to go.
You can go first.
15 minutes.
Okay. Well, let's go ahead and let's talk about redox then.
Okay.
Okay. I think other people would like to talk about
Yeah.
redox. We're also going
Yeah,
to talk
I
more
agree.
about redox tonight.
Good.
So we're going to talk more about redox reactions, but we did talk about all of the main things for redox
Is
reactions.
the stuff from tonight going to be on the midterm?
Redox reactions will be, because the stuff we do tonight is just going to be reviewing what we've already talked about redox, with an extra step of calculating
It's the,
oxidation
adding
limits.
electrons to the balancing equations, right? I think. I don't know. I was looking up stuff about redox reactions. And
You are doing Chem 128 balancing redox reactions in acid-base, acidic and basic conditions. We are not doing that till next quarter.
Okay.
So, good that you're looking it up, good that you're trying to find things, but you're finding stuff for like, you're finding like the most difficult redox questions, right?
Okay.
We're just doing the introduction to redox. And so the main thing that we want to do is we want to do some remembering of what redox means. This means reduction, oxidation, right? And in the past, these things were understood all in terms of oxygen moving back and forth. Where is oxygen going? How is oxygen affecting things? Oxygen was a good oxidizing agent that caused other things to get oxidized, right? And it was all about oxygen. Since then, we've learned that it's really about electrons, where reduction is the gain of electrons, and the oxidation is the loss of electrons. The abbreviation that I like for remembering this is loss of electrons, oxidation, gain of electrons, reduction. Leo the Lion says GER. The reason I think some people remember oil rig, which is like oxidation. Oxidation involves loss, reduction involves gain. I like Leo-Gerv because it puts the focus on the electrons first, right? You're losing electrons, you're gaining electrons. That's the first thing we think about. I'm going to do an example from something we saw in class last time, which is the Ki plus Cl2 aqueous goes to KCl plus I2 aqueous. Now, in order to determine if it's oxidation reduction, there's kind of two ways to go about it. First thing is to say, is it a precipitation reaction? No. Is it an acid-base reaction? No water product, no acid reactant? No. Must be redox. Now that I'm thinking it's redox, and I always like to do that beforehand, I find checking for redox reactions is the one that takes the most time. So I like to do that one last. Rule out the other ones first. I know that potassium has a plus charge, iodine has a minus charge, chlorine in its diatomic is 0, potassium has a plus charge, chloride has a minus charge, iodine in its elemental state is 0. And so from this, I can see chlorine here is gaining electrons. It's reduced. Right? Gaining electrons is reduction. And we made sense of the fact that it was gaining electrons because we could see that chlorine was more electronegative, so it could pull electrons away from other things. We can also see that it's going from a 0 to a -1. So we can do it just from knowing the common oxidation states, which we know from our periodic trends, which would be good to have marked on our periodic table. Now, you don't get to have your marked periodic tables during the exam, but as a study habit, hopefully you've already got a lot of these marks. So we can think about our periodic trends to understand why chlorine is more electronegative, why it's going to pick up that electron, our common oxidation states, right? All of these different ideas. One of the things that's nice about being in week 8 is we have many different ideas that all reinforce each other now. It's like it makes sense that chlorine becomes minus because it's more electronegative. It also makes sense that it steals electrons because it's more electronegative. Cl minus is the common charge of chlorine because it's got that one valence opening. Right? All of these ideas start to connect to each other. We've also got iodide here becoming iodine, where it lost an electron. It got oxidized. So in this situation, we've got our thing being oxidized, our thing being reduced. The chemical reaction is not balanced yet, so we can go ahead and balance the chemical equation now. We could have done it beforehand, but I wanted to point out why it was redox reaction. We want to have the same number of moles. Sneak in more, and if someone's willing, let's get another chair. So if we're balancing this, we're gonna look for making sure we have the correct number of reactants and products. So here I've got one potassium, that looks great. I've got one iodide, I've got two iodides, that's a problem. Okay, I need to balance all of my first thing to check, make sure all of your products and reactants are good compounds. So that means they're charge neutral, they're stable, and they're reasonable. I can't remember what my third thing is, I'm blanking on it. So plus minus charge neutral, 0 charge neutral, plus minus charge neutral, 0 neutral. These are the elemental states, these are the diatomic acids, they have the subscript 2.
What about oxidation state in general, finding the oxidation state?
That's what all of these things are.
But I meant, what are the rules again for that? That was the part I was having trouble with.
The oxidation states? Okay, so there's a set of rules that are on the slides. And so there were kind of a few things that we looked at. We're going to look at our common oxidation states and then figure everything out around them. So the common one was that if you have oxygen, oxygen almost always has a 2- charge on it. We don't have that in this case, so that doesn't matter. Hydrogen almost always has a +1 charge on it. I'm going to put actually 1 above this. Our elemental state is a 0 charge. So that is any of our metals by itself, magnesium metal by itself, iron metal by itself, aluminum metal by itself, any of our diatomic gases in pairs. So our Cl2, our I2, Br2, F2, all of those are zeros. Oxygen is -2, hydrogen is +1, and then our halogens, typically -1, not always. This one I'll put an asterisk next to. These first 3 are very reliable, like 99% of the time in this class reliable. This last one, 85% of the time reliable. So it was oxidation states, not redox reactions?
It was like a mix of both. I was like, for example, this, I did that earlier. That was.
We also did it in class as well. I was just doing an example. I didn't know where to start because you just said redox reaction.
Sorry.
So I was starting at the beginning.
What's the, like, why do we use oxidation state versus like just charge though? If
Let me get to that. Did you have a question about this as well? Or?
Yeah, so is this stuff all like the stuff you could find on this sheet, or
Yeah.
is some of it just critical thinking?
Almost all of it's on that sheet.
Okay, so
right?
whatever's on the sheet you just go with when you're.
That's memorizing, right? We want to make sure that we're thinking about why that stuff is on the sheet and how we can figure it out if we don't have access to the sheet, say, during the exam.
Oh,
Right? You don't have that sheet during the exam.
Okay.
You just have your periodic table during the exam.
Okay.
So
how would you recommend like to kind of know these if we don't have?
So this is from our periodic trends, right? The -2 state on oxygen, the -2 state on sulfur, the +1 state on hydrogen, the -1 state on the halogens, the +2 state on the alkaline earth metals, the +1 state on the alkaline metals. All of that's from our periodic trends, right? So if you're looking at your periodic table instead of that, pull up your periodic table instead of that.
Mm-hmm.
What's the charge on sodium? Na.
Na. Would it be +1?
Yeah. Why is it +1?
Is in the same section as hydrogen?
It's in the same section of hydrogen. It has the 1 valence electron. It has low electron affinity, low ionization energy. It loses that 1 electron. It's got that S1. So there's like 5 different ways we should be able to explain why sodium ends up with a +1 charge, right? And so there's all of that stuff from the periodic trends, fills in most of this. This is just me kind of reiterating things we should already know.
So then, like, that means like this section would be mostly 2-.
Depends on which column you're looking at. It's not just the whole section. It's just oxygen's column.
Oh yeah.
And why is oxygen's column 2-?
Because it has around the same electron affinity. Or-
Well, it's got the 2 openings in its valence shell, right? 2 steps to fill its valence shell, so it picks up 2 electrons, right? We can make sense of this. Why is fluorine -1?
Because
1 opening in its valence shell, right? It's 1 step away from having its full valence shell. Now, how are oxidation state and charge different from each other? For a lot of cases, I was just reiterating your question, not asking you to answer. For a lot of cases, and if people want to come in and sit on the floor in here, if you're comfortable with that, there's lots of space. I know he has to get going, so that's why he's trying to hover by the door. One of the, you're fine, they're scared to come in. One of the cases, in most cases, everything we've done up till now, oxidation state and charge have been kind of interchangeable, right? When you look at when we look at our ionic compounds, Cl has a charge of -1. It also has an oxidation state of -1. Na has a charge of +1. It also has an oxidation state of +1. So in those situations, those 2 terms are interchangeable. The place where we have to be careful is when we're looking at our covalent compounds. Let me think of one real quick. Let's do NO3 real quick. NO3-. So if we're looking at nitrate, if my oxygens are all -2s, then I'm going to have, what's the oxidation state on nitrogen, which is different than its charge in this case. Oxygens are all -2. I've got 3 of those. I want this to overall add up to a -1. and I've got my charge on nitrogen times 1. So I'll just go ahead and plug in an x here, solve for x.
5.
It's 5. It's plus 5.
So it's like, what is required of it to make it negative
Yeah.
1 equals
Yeah.
2, basically?
Yeah. Now, in this, does that nitrogen have a charge of 5?
No.
No, it's not actually going to lose all 5 of its valence electrons, but it's sharing all 5 of its electrons in such a way that it really doesn't have much electrons around it because of the oxygen attached to it, which is why we call it an oxidation state.
Because it's losing like 5, or not losing, but like bonding 5 electrons to the
It's
oxygen.
sharing its 5 electrons
Yeah.
away to the oxygen. And since it's sharing those 5 electrons away, the oxygen essentially pulls all of those electrons away from it because it's got higher electronegativity. And in that situation, in these covalent situations, oxidation state and charge are not synonyms anymore, right? The charge of this polyatomic ion is -1, but each thing in it has an oxidation state. Oxygen is a -2 oxidation state. Nitrogen is a +5 oxidation state.
So then, what part makes it like useful for what we're doing currently?
So when we're looking at, so nitrate is actually something that goes through redox reactions pretty powerfully, and the oxidation state changing is evidence of a redox reaction,
Okay,
right?
that makes more sense.
So it's the idea that the electrons that are spending time around nitrogen can be moved, right? Nitrogen could gain electrons and lose electrons. Well, in this situation, nitrogen could only gain electrons. But if you went through some reaction that produced like N2 gas from nitrate, your nitrogen would have to gain electrons and get reduced,
Yeah, okay, that makes sense.
right?
Thank
So
you.
it's that detailed difference in, and I think the reason that charge and oxidation state is confusing is because everything we've looked at up until our last class, until Thursday, they've been synonyms. We've only been looking at ionic compounds. It's like you can use them interchangeably in ionic compounds. When we start looking at the oxidation states on covalent compounds, charge and oxidation state are now different.
Sounds good. I'll see you.
Okay, I'll see you tonight, and we will talk more about this.
Sounds good.
So it is totally dependent on the charge, and when you're doing oxidation states, you always want to look at what it's like trying to be. Like I always aim for it to be neutral, and I
What-
guess that was a misconception.
So you want it to be whatever charge it is, right? So
Sure.
nitrate is a common polyatomic ion. So if we're looking at a common polyatomic ion, if we're looking at phosphate, let's say, PO4 3-,
Yep.
it would need to have the 3-. Now, you'll never make phosphate charge neutral by itself. You would need to have like sodium phosphate, right? And those 3 sodiums are where you can force it to be neutral. So it depends on whether the question is asking about sodium phosphate or phosphate, right? In both of those cases, we need to think through like, well, what's the question asking? Is this a common polyatomic ion where I need to preserve the negative charge because it's an anion? Or is it a ionic compound that should end up totally neutral? Or a covalent compound that should end up totally neutral, right? We always, like one of the big things I've been trying to emphasize all quarter since we first started learning how to name things, even before then, is we have to be able to identify whether it's a covalent compound or an ionic compound, because those behave in different ways, they get named in different ways, how we treat them is different, right? And the names are trying to communicate the fact that it is ionic or it is covalent. It's trying to give us that extra information. So we have to pay attention to that first, and then our logical progression can go from there. But it's almost always start with, is it ionic, is it covalent? Here, sodium phosphate, there's ionic and there's covalent. So it's not just a yes or no. We would treat the ionic part one way, we treat the covalent part another way. So that was reduction. Other questions about reduction oxidation reactions before we go back to balancing? That got kind of like roundabouty, but that's okay. So going back to this chemical equation, we need to balance this stuff. Now the essence of balancing is making sure that we have all of our atoms on the reactant side as the same number of product side. And after I have all of my compounds being good, charge balanced, stable, all of that stuff. Then we don't want to change the subscripts at all. Changing the subscripts will change the chemical compound. I don't want to change the chemical compounds anymore. I just want to change how much of each chemical compound there is. Just say I want to change the coefficients. If I've got two iodines in the iodide form and two iodines over here, we don't just want to put like a subscript 2 there because that would make this a bad compound now. So that would be no good. But we can put a coefficient out front. Now when I put this coefficient out front, it messes up my number of potassiums. So kind of in response or in the process, I put a 2 there. And then I check my chlorines. There's 2 chlorides, there's 2 chlorines. That's balanced. If we're doing it correctly, you should find things reinforce each other in that way, where like one leads to the other, leads to the other, leads to the other, and it's like, oh, it's okay. Should we try a harder one?
Sure.
Okay. Now we'll do some of these harder ones tonight in class as well. We just kind of, we've just got some of like the easy balancing to start, but let's do a kind of hard one. Okay, let's first step is predicting products. I've got C2H6 and O2 gas. If you did the prep activity, you should be able to predict the products of a combustion reaction.
CO2.
We're going to make CO2. Somebody else, what's the other thing you make when you burn things?
H2O.
Yeah, an H2O. Usually in the gas state because there's a lot of heat around as well. What type of reaction is this? So there's only our 3 categories. Is it acid-base? Well, let's do the easy one first. Is it precipitation?
No.
It's not precipitation. There's no ions. There's no solids being formed. Is it acid-base? There's water as a product, but there's no acid reactant, right? I don't have one of my super polarized hydrogen things as a reactant. I don't have any acid. So it's not acid-base.
Oxidation.
It's an oxidation reaction. Here's the other way we can tell. Oxygen is getting added to something. That's oxidation.
Oh.
Right? That is the traditional, that's like the historical definition of oxidation is adding oxygen to things. So here, carbon without oxygen, carbon with oxygen, carbon's been oxidized. Right? So we can see that right there. We can now go ahead and figure out how we balance this. It's a redox reaction. We can look at the change in oxidation states in a minute to figure that out if we want. But first, let's just balance it. Now, this one is going to be a little bit tricky to balance. I'm going to balance in a different color, and then I'm only going to switch to black when I've got it all correct. So, 2 carbons. I'm just going to put a 2 here, 2 carbons. That looks great. 6 hydrogens. I'm going to put a 3 here. That gets me 6 hydrogens. Great. 2 oxygens. There's 4 oxygens. 5, 6, 7 oxygens. Does anyone see the problem here? It's odd when I've got an even number over here. It's never going to work if I do it this way. So I'm going to double everything. I'm going to make this 2. I'm going to make this 4. I'm going to make this 6. Now over here I've got 4. I've got 4 times 2 is 8 plus 6, 14. 7 there would balance it. Now I'm going to go ahead. I'm going to do the long table way since people are still working on this, and this was kind of a tricky one. I did it pretty quick, but then I'm going to do my long version of checking, which I get out of pretty quick. I'm going to have my products. Sorry, products are second. I'm going to have my reactants. I'm going to have my products, and I'm going to check. And I've got carbons, hydrogens, and oxygens. That's all I have to check. But I'm going to check all of those. 4 carbons in my reactant side, 4 carbons in my product side, right? Because 2 times 2, 4 times 1. Hydrogens, 2 times 6 is 12. 6 times 2, 12. That looks great. Oxygens, 7 times 2 is 14. 4 times 2 is 8. 6 times 1 is 6. 14. Right, I'm just checking to make sure I've got the same count of atoms on my reactant side and my product side. 4 carbons in the reactants, 4 carbons in the products. 12 hydrogens in the reactants, 12 hydrogens in the products. 14 oxygens in the reactants, 14 oxygens in the products. Right? And so that is the essence of balancing. Because chemistry does not create new atoms, it just rearranges the atoms that are already there. Let's see. Let's go ahead and do the net ionic equation for this one as well. I think this is a silly one to do. Does anyone see why this is a silly one to do a net ionic equation for?
Because it stays in gas.
Everything's gas form. We're not going to have ions. But what do we write for the net ionic equation in that case? Is it okay if I erase this part?
Yes.
Let's first get our balancing coefficients in here. 2, 7, 4, 6. It's just the same equation, right? There's nothing to cancel out. The original reaction we wrote down was already the net ionic. That happens very often when we're doing reactions in the gas state, or we're doing reactions with mostly covalent compounds, no ionic compounds. Nothing gets canceled out. So, totally possible that the chemical reaction you wrote down was already your net ionic equation. Yeah?
I know that one's the same, but can you like explain like the difference of like when you need to change it? Like to say that it's not the same? 'Cause
Let's go ahead and do, let me see if I can think of one. Yeah, we can do one. Is it okay if I erase this? How complicated do you want the example to be? On a
Not
scale
like
of-
easy, but not like super hard.
Okay, let's try,
8 ends.
I'll do 2. I'll do one that's kind of, I think, medium difficulty, and then do one that's like really, like what the heck are you doing? Okay, so I'm going to, do I have the, okay, there we go, hydroxide, okay. So we're gonna go ahead and mix aluminum, oh yeah, let's make this a little bit more complicated. No, let's not make it too complicated. We're gonna mix aluminum chloride with, what did I want to do? Yeah, let's do that. No, not that complicated, not that complicated. Let's do potassium. With potassium hydroxide. That's a capital O. Be careful with your lowercase o versus your capital O. Hey, come on in. If you're comfortable sitting on the floor, you can do that, or if you want to sit on the desk, or just that's fine too. Okay, so we're just doing an example. We're not really doing redox anymore. We finished that. This is not ionic. Right. So first thing we do, predict the products. Well, actually, first, well, yeah, let's just predict the products. What are we going to do?
Flip-flop.
Flip-flop. Okay, so I'm going to take my aluminum, put it where the potassium is, take the potassium, put it where the aluminum is. So I'm going to get potassium chloride and aluminum hydroxide. Then I'm going to go ahead and make sure that my compounds are good. Aluminum has a +3 charge, that's why it's got 3 Cl minuses on it. Potassium has a +1, that's why it's got the 1 hydroxide. So over here, potassium chloride is good. This aluminum hydroxide, I need a subscript 3 on the hydroxide, so I had to put parentheses in. We only put parentheses on polyatomic ions when there's an additional subscript to communicate a certain number of that polyatomic ion. So there's my aluminum hydroxide. All my compounds are good. Now I can go ahead and check states of matter for all of these things. Who's got their periodic tables handy?
Aqueous was the first one.
Yep, chloride compounds are soluble. There's a couple exceptions. Aluminum's not one of them. Hydroxide compounds, generally insoluble,
Except with K.
except for with that first row, first column. So that's going to be aqueous as well. Potassium chloride, we just said potassium compounds are usually soluble, so that's going to be aqueous. And then aluminum hydroxide.
So.
I'm going to wait for more people this time. I've been going too fast. How many of you are just waiting for me to tell you what the answer
Is
is?
it soluble? Or no?
It's one of the two. Soluble or no? Got to make sure we know how to read these rules. Okay, so let's read it together. I see enough people kind of getting to the right thing now that I'm going to believe you're all working on it. Rule number 1, insoluble ionic compound says hydroxide is insoluble except with group 1 and larger group 2s. Aluminum is not in group 1 or group 2. That means this is not one of the exceptions. That's going to be solid. What type of reaction is this? Is it acid-base? We've got a base, but we don't have an acid. We don't have water as a product. It's not acid-base. Is it precipitation? And we're going from aqueous ions to a solid forming. It looks like precipitation. Is it redox? Probably not. Right? We already know that it's precipitation. There is the possibility of having reactions that are both acid, that are more than one of those categories. Not something we're going to run into very often this quarter, but it's possible to have something that's more than one. Did you get your question answered?
Yeah. I just came to practice.
Oh, okay, cool.
Thank
See
you.
ya. So we can go ahead and we can now start to balance this chemical equation. This plus is, I didn't have enough space and I can't figure out the best place to put it there. Okay. 1 aluminum, that looks great. 1 potassium, that looks great. 1 chloride, 3 chlorides. I can't change my subscripts, that would change my compound. So I'm going to put a 3 out front here. Now I've got 3 chlorides, that looks great. 1 hydroxide, 3 potassiums, 1 potassium, 3 hydroxides, 1 hydroxide. 3 out front here is going to take care of it. That gives me my 3 potassiums, and 3 hydroxides, 3 hydroxides. And it's often very nice to balance in terms of your polyatomic ions. I don't have to balance the oxygens and hydrogens separately. I can just say, look, hydroxide's not changing. It's hydroxide here, it's hydroxide there. I can balance the O's and H's together. Doesn't always work out that nicely, but that's that case.
Can you explain one more time why you put the 3 subscript by the OH in the product side?
Yeah, so over here, when I was looking at this, it was because I was figuring out the oxidation states, the charges of these different things. I know chloride, as my typical rules, chloride is a -1. So that means in order for this compound to be good, and I gave you that subscript, in order for this compound to be good, aluminum must be +3. And it turns out when we look at our common cations, aluminum is almost always a +3. It's not one of our transition metals. It's outside of the transition metals. It's really predictably a +3. So that looked good. That means the aluminum over here also likely to be a +3 unless it's a redox reaction.
Okay.
But I knew it wasn't a redox reaction, so we went with that. If that's +3, we have to have 3 hydroxides to get my 3 minuses to make it a good compound.
Yeah.
Question?
When it comes to memorizing common nomenclature, knowing that aluminum is almost always +3, is that like important to actually know, or can we just rely on our ability to deduce it from the balanced equation?
Well, you can't balance the equation unless you have good compounds. So knowing that aluminum is +3, not by memorizing, but by understanding the periodic trends, the number of valence electrons, how many electrons it loses to become stable, that's where you want to be thinking. If you look at where aluminum is on the periodic table,
Is it in the middle?
it's right below boron.
Oh.
Right? So if you look, again, having your periodic table handy is useful, but
Yeah.
you have the option of gaining 1, 2, 3, 4, aluminum -5. We'd get it to its valence shell. But it's not very electronegative, so gaining 5 electrons seems really unlikely.
Yeah.
Losing 3 electrons, much more likely. Also, not reacting. Aluminum is a metal that we find pretty often, right? Part of why they make cans out of it is because
Abundant.
it's abundant and relatively stable. But if we had aluminum in the +3 state, actually, okay, this was a thing I heard when I was a kid, and apparently people don't hear this anymore. Did you ever hear the idea that recycling an aluminum can saves enough electricity to run your television, your cell phone for like a day? That was like something I heard when I was younger, and it never made sense to me. It turns out that to make aluminum metal, we actually find aluminum ore, which is aluminum oxides and aluminum in the +3 state. It's these different aluminum rocks that's not like metal, but then you can run electricity through it and you can force electrons onto aluminum and turn it into aluminum metal, but it takes a lot of electricity. Question?
So what does the potassium get in a 3 when you're balancing?
Where?
Both in the reaction and the product.
So when I look at the charge on hydroxide here, hydroxide has a charge of -1.
Yeah.
Potassium has a charge of +1.
Yeah.
So that is already a stable compound. So I don't want to change the subscripts, I just want to change the coefficients. Now I needed the 3 here, this plus, this minus, because I needed to have the 3 chlorides to balance the 3 chlorides here.
But do you not identify the 3 chlorides in the product? Like, do you not have to put a subscript 3 on the chloride?
If I put a subscript 3 here,
Yeah.
then this compound's not good anymore, right? Because it's +1 -1. Right, so the thing that becomes important to keep in mind is, what does AlCl3 actually look like? What is going on there? So when we think of AlCl3, that's going to be like an aluminum +3 ionically bonded to 3 chlorides. And going for net ionic, maybe this will help make sense, because when we start looking at the net ionic, it's not like it's a Cl3 compound that's moving around. It's 3 chlorides that are associating with 1 potassium. Right, since the potassium is a +1, I'm only going to have 1 chloride for each potassium.
Okay.
So I put the coefficient through. Like KCl is a good compound; it's charge balanced.
Okay.
The 3 out front says I'm going to need 3 KCl's in order to balance out the other side. So let's look at what this becomes when I do my total ionic versus my net ionic. So there's my reaction. If I look at my total ionic, I'm going to follow those rules of ionic compounds break apart from the solubility rules. Metallic solids, pure liquids, and gases are not going to break apart. They might change state of matter. They might be aqueous, they might be gas, they might be liquid, but they're not going to break apart. Ionic compounds depends on the ionic compounds list for whether they're soluble or not. And then covalent compounds do not break apart unless they're strong acids. Right, so those are the 3 things to look for. Here I've got an ionic compound that we've already identified as aqueous. So that's going to break apart into Al3 plus aqueous plus 3 Cl minus aqueous. And switching from it being a subscript to being a coefficient is recognizing that it's not a Cl3 compound. It's 3 Cl minuses that are associating with the aluminum. So this is giving that kind of recognition to how the ions exist in solution. Same thing happens with my potassium hydroxide. This is an ionic bond, so it's going to disassociate. The O to H is a covalent bond, will not disassociate. So I'll get 3K plus 3 OH minus. The common mistake I see here is people try to break up the O into H. So they do 3K plus, 3O, 2 minus, and 3H plus. It's like, no. The ionic bond breaks apart. What we do, if we want to sound more scientific, we say the ionic bond disassociates. The covalent bond does not disassociate. So the ionic bond between the potassium and the hydroxide falls apart. The covalent bond between the oxygen and the hydrogen in hydroxide stays together. Now I didn't give myself enough space, so I'm just going to go down instead of across. KCl, ionic bond, will break apart. Give to be 3K plus and 3Cl minus. Aluminum hydroxide, ionic compound, but we already looked at the solubility rules and said it's not going to disassociate, it's going to stay a solid. So we're just going to leave that as a solid. AlOH3 solid. Now, we cancel out anything that is the same atom with the same charge and the same state of matter. All three of those things need to be the same. We'll cancel those out because those are not changing, right? 3K plus aqueous, 3K plus aqueous. What's that mean? I had potassium ions floating around in solution, got a potassium ions floating around in solution. They didn't change when I mixed things together. That's not going to do anything interesting. Aluminum was ions floating around in solution, became a solid. That's interesting. Don't get rid of it. Chlorides, Cl minus aqueous, Cl minus aqueous. That didn't change. That's not very interesting. Now we can get to our net ionic. So I'm going to keep those things that actually change. So it's Al 3 plus aqueous plus 3 OH minus aqueous goes to Al OH 3 solid. Right? And so that net ionic equation, when we go deeper into understanding chemical reactions, the energies associated with them, the equilibrium of them, the extent of them, these abbreviated where I'm just focusing on what's chemically changing, that's going to be more useful. How many of you are going to take Chem 129? A couple of you. We're going to use these net ionics a lot in Chem 129. For us now, it's just kind of accentuating those things that chemically change, that are doing something chemically interesting. What this tells me is, it doesn't matter how aluminum gets in solution. If it bumps into hydroxide solution, however the hydroxide got there, those two things bump into each other, they're going to form a solid that doesn't dissolve. They're going to form a precipitate.
When doing the net ionic, do you recommend going through the whole process every time, or
Almost.
if you can,
Almost
okay.
always, right? Once you practice it a lot, you'll get better at it. One of the tips to keep in mind is the aqueous product is going to be the ions you cancel.
Yeah.
Right? The solid product is going to be the things you keep. So once you practice this a bit more, it goes really well. But I still do it the long way pretty often just to make sure I'm not missing things.
And it's not just solids, right? It's just like whatever state changes in the product
Yeah.
is what's going to be in the net.
Yeah, so we can see the same thing happen if we see like gases get produced or pure liquids show up, things like that.
Yeah.
For this class, most of the time it's going to be solids.
Okay.
Yeah.
Do you think you could give us like a brief outline of what exactly is going to be on the exam?
Everything since the first exam, plus things that were necessary from the first exam. So let's see, what is that?
I have an easier time studying when I know like exactly.
The exact list is really long. So this is the problem I have with making these study lists, is I'm like, periodic trends, types of reactions, bonding. But there's so many subcategories that you can put underneath each of those that it can become a really long list. So right when we were finishing, and for me, to really get a complete list, I have to look through all of my lecture slides and make sure I don't miss anything. So I can give you like the things I can think of off the top of my head, but
Yeah.
like,
I
without going through all of my lecture slides, I might miss something.
Okay, because I started like studying like Rydberg and like wavelength and stuff.
Yeah.
I don't know if that's gonna be on the exam.
So I would say I'm going to focus on the new material, probably like an 85-15 split. 85 to 90% of the material will be the new stuff, 10 to 15 on the old stuff. When we get to the final exam, completely cumulative, we'll talk more about that later. The thing you have to watch out for, and the reason I don't just say it's only the new stuff, is because we talked about electron configurations and periodic trends before the first midterm, and we still need that stuff to keep doing the work we're doing. We talked about atomic structure, like number of protons, number of electrons, number of neutrons, before the first exam, and we still need that stuff. We talked about molecular weight and molarity before the first exam.
Yeah.
We still need that stuff.
Right.
So, mostly new stuff.
So it's like week 5 till now.
Week 4.
Week 4.
Because the Tuesday that we did on week 4 was not, Like the Tuesday we did in week 4 was like half review, half new stuff. And the half that was on new stuff was not on the first exam. The half that was review was on the first exam, but was probably stuff we still need for the second exam because it fed into the stuff we did after the exam.
Okay.
Does that make sense?
Yeah.
So, thinking back, not quite all the way back to quantum numbers, but you need quantum numbers to do electron configurations. You need electron configurations to get the periodic table. You need the periodic table to get the periodic trends to get electronegativity, to understand ionic, covalent, metallic. We spent some time on ionic. We didn't spend much time on covalent. On metallic. And then we did a bunch of time on covalent. We built covalent compounds. We talked about geometry. We talked about polarity from electronegativity, which was back to the periodic trends again. I know I'm forgetting some things. We talked about resonance structures, isomers, Vesper, the different geometries, the thing we did with the string.
Yeah.
Resonance structures, we talked about bonding and the bond length, bond strength, and then we said, hey, if we get extreme differences in electronegativity, we can start looking at reactions. And so, sorry, whoop, skipped a whole section there. We went from geometry to bond polarity to molecular dipoles to intermolecular forces. You can talk about the 5 different intermolecular, 3 to 5 different intermolecular forces, depending on how detailed you want your list to be. You have your 5 intermolecular forces. We really only focused on 3. Went from intermolecular forces to talking about chromatography, paper chromatography, gas chromatography, boiling point, solubility of covalent compounds. And then I think I'm finally at the point, I might have skipped 1 or 2 things in there, but then you go from solubility of covalent compounds to talking about ionic compounds and how you can have that ion-dipole interaction, that strongest intermolecular force that we didn't care much about until then, to talk about why solids dissolve in water or not. And we used that to get our ionic list, and then we started talking about precipitation reactions. Then we did acid-base reactions as a specialization of like somewhere between covalent and ionic. We then did our net ionic equations, predicting solids. Then we did our types of reactions, redox reactions, and then we did the lab.
So for my studying, I've been doing redoing the homeworks and going over the quizzes.
Okay.
Is that an effective?
That's effective for the online portion of the exam.
For in-person, would it just be slides and textbook?
Mostly, the writing activities we've been doing,
Mm-hmm.
you need to make up your own questions with friends.
Okay.
Right? You need to, the doing problems like the homework and all that, most people skip the problems I have on there that are like, explain this to a friend. Because there's not a box to click on, so they don't do them. But those concept questions are really, really important in this set of material. Right? There's not a lot of calculations. There's not a lot of number crunching. So there's can I explain ideas in a coherent way that makes sense to my classmates, that would make sense to the instructor, and would get me credit. So redoing the quizzes, one of the problems with redoing the quizzes and the homeworks is if you've already done them, you're repeating problems you've already done. If you've already got them right, doing them again doesn't really help you. So what you have to start doing, did you watch my study tips video?
Yeah.
Okay, so the big thing that I mentioned in that towards the end was one of the important ideas is looking for the understanding and the analyzing steps, not just the remembering steps. Right? So after you do 3 or 4 problems, can you look at those 4 problems and understand why they're clumped together, what they have in common, what they have different, and can you explain similarities and differences, key terms that make it so they are the same or they are different? And can you explain that to somebody else? So looking for those broader kind of can I look at a set of problems and make sense of it? Am I just memorizing things and applying it like a hammer, or can I design what's going on and understand it further? And that's where studying with other people and practicing writing becomes really important. How do you all feel about those writing activities I've been doing?
I like it.
Basically.
Challenging, okay. But useful? Okay. So I've been kind of torn about it because I thought it was really useful. I thought it was really interesting. one of the things that I've had people complain about in my class in the past is they don't have any practice doing the like, my free response questions catch them completely off guard because I've never asked them to write down explanations for things. Like it doesn't really happen in the homeworks. I assume they're doing it with each other, but I've never done something where like, no, you have to write an explanation. So I feel good doing it, but man, I have to tell you about a third of the students write like 4 words in 10 minutes, even though it's open note. About a third. I'm just like, I gave you 10 minutes for that? And then when we do the 10 minutes where they're working together, you all know you got people like this in your cluster. Do the 10 minutes working together, and there's like one person who's just like, oh, you just write the thing you have, it's good. And like, there's people in the cluster who are not contributing, not even reading what you wrote to be like, oh, can you explain that to me? They're just like, I wrote my 3 words, whatever. It's not worth any points, but like, I'm trying to do this to get people to be like, can I actually write an explanation? So I'm kind of, so like, for me, it kind of is at that point where I'm like, is this a good use of 20 minutes of class time each week-ish? For some of you, yes, right? And like that third of students who are not engaging with it, I'm really nervous about the midterm on Thursday for them. We'll see how it goes.
Will stuff from today be on midterm?
Kind of, right? So stuff from today, we're going to be, the first like bit of class is going to be looking at redox reactions with more detail, and redox reactions can be on there. So looking at redox reactions with more detail, going into oxidation states, and then getting into stoichiometry. And the stuff we talk about with stoichiometry will not be on this exam. But like everything we did last week up through redox reactions will be. Question?
What about math-based questions from like, for example, last midterm there was like a question about a cylinder, trying to find the measurement between 100 milliliter marks. Do we have to worry about that?
I'll give you all a clue, and people who watch this will have this clue as well. I'm going to put one question on the online portion that is from the old material. And I think that's going to be the only question that's going to be one of these math-based questions from the old material. And my clue for you is, it's a question that as many times I've put it on there, it still is only at 45% correct.
Redbird maybe, or
That is all I'm going to say.
It's the wavelength one with the,
It's
with
the-
the
Yeah.
watt, the 2 seconds, like the lamp.
That is the
It's the
extent
N
of
from
my
1 to 5, I
Yeah.
think.
sure. That is the
Sound
extent of my hint.
It's
You
like
can
a-
all look at the past quizzes
You
and you
have it
can
in
figure
every
out there's a
quiz.
quiz. Was that?
You have it in every single.
You can
quiz.
find out there's a
Is that the
question that's
extent of
been
math,
on
though?
every quiz besides the
Is it
first
the
one.
lamp?
Yep.
Like the UV, like the watt.
I'm trying to find
It's
it.
absorption.
Like 2 seconds.
No, I think it's the one where you're trying to find the level of
Yeah.
gaining or losing from like
It's
1 to
gonna-
5, n equals 1
and
and n equals
that kind of
5.
stuff.
But it's
Is that the
gonna
extent
be
of math
absorption.
though? Like, is that like the main math stuff we need to know, or?
I would have to double check everything, but we
Okay.
haven't had much math. So
That's
I
yeah.
think
That's the main thing I'm worried about.
So yeah, that is the extent. If you all want to do some problems from past quizzes and see if you can figure out like which one, I won't say which one it is. But there's a question that I've put on a lot of quizzes and a lot of assignments, and it's only at 45% correct. It's been somewhere between like 30 and 40% correct since the second quiz. And that means there's a third of the class that's just been getting free points on every assignment for the last 5 weeks. And then there's another like 70% of the class that's like, why would he's not going to do that again. And it's like, no, I'm going to keep doing it until you get it right.
Do you think we could go over one of those ones where they give you the
Where you have to flip.
wavelength and...
You want to do a
meters?
question from quiz 5?
I don't have my computer on me, it's out there right now, but
Let's-
it's one of
let's
the ones
do-
where it's like from n equals 1 to another.
Sure, we
And
can
one of the
try
ones
one
where
of
the
those.
parentheses flips, maybe?
Yeah, we
Yeah.
can try that. What's that question? Do you want
But
to?
it's the absorption one.
We can try an absorption question from
Awesome.
quiz 5.
Awesome.
It was also on quiz 4.
Yeah, and every other.
I think I have a-
But that there's several. There's more than one question that's been persistently wrong. But there's one that I'm just kind of like has been really persistent. Like some of those other questions that were mentioned in the room, Like there's many, all of the questions that were mentioned in the room that people were guessing for like math questions that have been getting wrong a lot have all been somewhere between like in the last few quizzes have been between the 40 and like 60% correct range. I usually put questions on the exams on the quizzes and exams until they're above 60% correct. So like, but there's like 4 or 5 questions and I can't keep fitting them all on. So, but we can try a few. So like, go ahead and read the question.
I can give mine. So absorption of a 1.2819 times 10 to the third power
Nanometer.
photon raises an electron and hydrogen from n equals 3 to which quantum number n?
Also, if you watch the office hour videos, if you watch the office hour videos, I've done this one in the office hour videos 4 or 5 times as well. So let's go ahead. So first thing is we realize I always start whenever
2819.
2819. Thank you. 2819. That would have messed things up. Okay. So we got an absorption of a 2.189 photon. Raises a hydrogen from n equals 3 to n something. First thing I think about is my energy scale. Let's make that nice and long. Here's my n equals 1. Here's my n equals 2. Here's my n equals 3. Here's my n equals 4. Here's my n equals 5. Here's my n equals 6. Here's my n equals 7. Here's my n equals 8. N equals 9, and I'm tired of writing them, right? It keeps going. Now, this is going to start at n equals 3, and it's going to be absorption. So I know it's going to be going up, but I don't know how far it's going to be going up. Depends on the energy of that photon, but I know it's going to be absorption. Now, as soon as I see it's asking for 2 n values, my brain goes, oh, whose equation? It's going to be the Rydberg equation. So this is going to be the change in energy of the atom is equal to negative RH z squared 1 over n final squared minus 1 over n initial squared. My delta E of the photon, sorry, not the delta E of photon, just E of photon. Energy of the photon equals hc over lambda, and my energy of the photon is equal to the absolute value of the change in energy of the atom. Okay, so that's my kind of 3 equation bit for doing that question.
Is this supposed to be negative RH, or is it a negative Z and then RH?
Either one, right? I changed the order because I've had students who, when I write negative Z squared, they've been putting the parenthesis there instead of there. And I feel like it's the whole side is negative, whether it's the Z is negative or the RH is negative, and I just want to make sure we don't square that negative sign away. That negative sign needs to be there. We can simplify. I'm going to start with simplifying this thing. Right, I can have my delta E of the atom is equal to RH is going to be negative 2.18 times 10 to the minus 18. Z squared is going to be, since this is hydrogen, Z squared is going to be 1 squared, which is 1, so I'm just going to leave that gone. My 1 over n final squared is what I'm trying to figure out. My n initial is the 3 squared. Okay. So I can't go any further with that one because I don't know n final. I don't know the change in energy of the atom. So I'm stuck there. Then we can go ahead and say, well, I can figure out my energy of the photon. So I can get my energy of photon is equal to 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8th divided by 2.1819 times 10 to the 3 times 10 to the minus 9. Right, and that 10 to the minus 9 is getting rid of the nano. Yeah, nano. Right. I was like, negative or positive?
Is it 1.2?
Oh, goodness. That would have been a problem. Thank you. So I can go ahead, I've got a calculator someplace here, I can calculate my photon energy, 6.626 times 10 minus 34 times 2.99 times 10 to the 8th. Wait, I typed something wrong. 6.626 times 10 minus 34 times 2.99 times 10 to the 8th. That looks better. Divide by 1.2819 and I get my energy of photon. Double check my calculation, make sure I didn't make a mistake. I had at least one typo. I think I fixed it. 545 is 10 to the minus 19 joules. Right, 10 to the minus 19 is the scale we expect for our photon energy. It's a little bit on the small side, but it's a pretty long wavelength, so that makes sense. Right, it's 1,000 nanometers. That's bigger than we usually see. That wavelength would be like in the infrared, so lower energy than visible. Okay, now this is the part that really messes with people. So how do we deal with that absolute value? I can't just set this number equal to that thing and say I'm good, because I need to take the absolute value of something that I don't know if it's going to be positive or negative. But there's a way we can figure out if it's positive or negative through our logic. Is the photon gaining energy or losing energy? It's gaining energy, so the change in energy of the atom is positive, so I can just drop the absolute value, don't get rid of the negative sign, right? I already know it's going to be positive, so I can just go ahead and say, I'm going to get this equation. I'm going to erase this n equals 1 because it doesn't matter, I just drew it for consistency. I'm going to have 1.545 times 10 to the minus 19 is equal to negative 2.18 times 10 to the minus 18 times 1 over n final squared minus 1/9.
So whenever it's raising from n equaling one number to another number, you can just assume it's going to be positive?
Well, we know it's going to be, we know the change in energy of the atom is positive because going up in n values is the atom gaining energy.
Right, and that's
So it's going up,
raise,
yeah,
right?
So,
So,
yeah, exactly.
okay.
So whenever it's absorption, we know it's going to work out like this. Question?
So then if it was asking for an emission cone,
We would drop the
We would
negative
drop
sign
negative.
because the absolute value, because we know the atom would be losing energy, this delta E atom would be negative, we got to drop a negative sign to get rid of it. Now the reason this looks weird where I did an absolute value but I end up with a negative sign left over is because this thing is also going to be negative, and the negatives will cancel each other out. And that's the part that really messes with people. Because they see absolute value, they're like, get rid of negative. It's like, whoa, 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 whoa. It's the total thing that's negative. And we don't know right now with the energy up here, we don't know if it's negative or positive because we don't know what our end final is. But because it specified absorption, so if this problem didn't say the word absorption, it would actually be impossible. If it didn't say absorption or emission, it just said a photon, oh no, it's really hard to phrase that. You'd have to say a photon interacts with, no, it's really hard to word it where it's ambiguous. I don't know how you'd word it where it's ambiguous. A photon of this wavelength and a hydrogen atom, what's the end value? Like you'd have to leave out any words as to whether it was absorbed, emitted, interacting with, emitted from, like it's really hard to word that weird. But now we just solved this equation. I do a couple things to make it easier for me mathematically. Is it okay if I erase this stuff up to like this stuff in blue and just solve this equation now? Everyone's okay with that? Okay. So once I've got this figured out, like now I'm just doing the algebra. And hopefully we can all do the algebra, but there's a couple ways, there's a couple steps I take that I feel like make the algebra easier. I'll keep doing it in blue just for consistencies. First thing is I bring my negative sign in. I don't like negative signs. So I bring my negative sign in. So I've got my 1.545 times 10 to the minus 19 is equal to, let's divide that 2.18 over as well. 2.18 times 10 to the minus 18 is equal to 1/9 minus 1 over n final squared. Maybe I didn't want to do that now that I'm looking at this. No, that's okay. That's okay. That's okay. So I can go ahead. So I did it. I divided this over. I brought the negative sign in. That's what changed the order. Since I know n final is bigger than 3, this parenthesis is going to stay positive. Right? Because 1/9 minus 1/16, 1/9 minus 1/25, 1/9 minus 1/36, 1/9 minus 1/47. Always, that second thing is going to be smaller, so it'll always end up positive. Let's do this real quick. 1.545 times 10 to the minus 19 divided by 2.18 times 10 to the minus 18. And this gets me like 0.070872 is equal to 1/9 minus 1 over n final squared. Next thing, because I, again, don't like negative signs, I'm going to add the n final over and subtract the 708 over. So I'm going to get 1 over n final squared is equal to 1/9 minus 0.070872. Right, so I just traded those places by subtracting and adding to both sides. And that's going to give me 1 over n final squared is equal to 0.0424. Equal to 1 over n final squared. Then I go ahead and I cross multiply, so I have 1 over 0.04. Whoa. I'm dropping zeros. 4024. 4024 is equal to n final squared. Inverse this side. Inverse. And I get 24.85 is equal to n final squared. Square root 4.989. It's supposed to be 5. And final equals 5. Now, to check this, I can plug 5 in here and see if I get that number. So if I do all this and I'm like, well, did I make a mistake? I can plug 5 in here and see if I get the same number. If I get the same number, I'm good. If I get a different number, if I get a negative, something like that, problem. Question?
I've seen like YouTube video examples where it's like instead of doing like the HC over lambda, they do 1 over lambda, and then they convert nanometers to meters, and then they use the Rydberg constant.
They use a different Rydberg constant.
It's like 1.097 meters.
Times 10 to the 7.
Yeah.
Yeah.
Does that work as well?
Yeah.
But this is.
There's a bunch of different things that go into making that work that we did in this process. Right? This process takes care of all that. So that number they use for the Rydberg constant is 2.18 times 10 to the minus 18 divided by HC. Right? They just divide the HC over to get the new Rydberg constant. Why memorize 2 Rydberg constants or like have 2 Rydberg constants when they're just one is the other divided by HC? The other thing for those examples that's really important that they always forget to mention, they call it N1 and N2 instead of N final and N initial. N1 has to be smaller than N2. So they're doing the absolute value in a different way. But they still need the absolute value. They do the absolute value, and they also drop the negative sign. Right? They drop the negative sign and then force the parenthesis to be positive by saying N1 has to be smaller than N2.
Because I was doing like that way, and I just kept getting it wrong.
Yeah, so there's like 3D. If you watch these videos that just use that equation but didn't explain the details of that equation, there's some details that are really important.
Okay.
The main one that probably was getting you wrong is it's not N final minus N initial. It's N1 minus N2, where N1 has to be smaller than N2.
Okay.
And that has to be smaller is doing the work of the absolute value.
Okay. Sweet. Thank you.
Hey, you bet. So this is a problem that people are still getting really wrong. There's a couple of other problems that we can do those as well, but this is a problem that people are still getting wrong.
This is the type of problem we should probably prioritize studying over other math problems, you'd think?
From the old material.
Yeah. Gotcha.
These types of problems. And then there's other, like I said, this is not the only one. I'm not saying this is the problem. But this definitely falls into that category of problems that people have been missing a lot.
Yeah.
There's still a couple other things we haven't talked about. How are people, so that was a sidetrack from, we talked about redox, we talked about balancing. Did we do enough balancing and net ionic equations? People feeling better about that? Like I said, we're doing more tonight as well. Okay. Polarizability. I think the person who asked about that took off. I'm going to talk about it briefly. I mentioned it during class. Polarizability is a fancy way of saying how easy is it to push the electrons around. So let's go ahead and talk about polarizability. There's many different factors that go into making something more or less polarizable, but there's one important feature that we've been using as a shorthand for polarizability, that when I say it, you're going to be like, oh, that's what it means? So polarizability is how well the electrons in a molecule get pushed around to disperse the electrons in a dispersion force. So there's many different factors that go into polarizability. The main one we've been worried about starts with an S, ends with an surface area. So polarizability, the shortcut we've been using to talk about polarizability is surface area. That's kind of one of the big tells for how polarizable something is. So polarizability has a lot to do with the London dispersion force. The larger surface area a molecule has, the more polarizable it is, the stronger the London dispersion force. Now, this is why something like an ion, right? So when you have something like NO3 minus, it's an ion. It still has London dispersion force because it still has even though it's got this minus charge, that minus charge can be pushed to one side or the other. So it still has polarizability. But it also is going to have ion-dipole interactions, so the London dispersion force is probably going to be minuscule compared to the other forces present. So in ions, we usually don't worry. Even though it has London dispersion force, it usually doesn't matter. It's just most people, when they think about polarizability and making one side negative, one side positive, it's really weird to them when they're looking at something that is charged. Now this, I just realized as I was talking, this is a bad example, because if we draw the Lewis structure for nitrate, it looks like, I guess it's not a bad, that's kind of a bad example, right? Nitrate's a weird one where we've got a plus charge on the nitrogen, the minus charge is on the oxygen. Did I forget something? 2, 4, 6, 8. I think that's right. I should go through the whole process to make sure I did it correctly. I gotta go. I don't want it wrong on video. Let's go ahead and double check this. Nitrogen is 5 electrons. Oxygen is 6 electrons, and I've got 3 of them. I've got the -1 charge for 1 more. That's going to be 18 plus 8. That's going to be 26 electrons. 4, 8. No, 8, 16, 24. Is my math wrong here? Yeah, my math is wrong. That's 24. Math is hard. 18 plus 6, not 18 plus 8. 24 electrons, 4, 8. 8, 16, 24 electrons. This looks good. Check the formal charge to make sure I've got the formal charge correct. I know I got the oxygens right, but I want to check the formal charge on nitrogen. That's going to be 5 minus 0 minus a half of 2, 4, 6, 8. Plus 1. Okay, great. I did have the right structure. I just wanted to make sure. So that's going to be the Lewis structure. This is going to have trigonal planar geometry. It's not going to be polar, but it will be polarizable. That is to say, well, you can still push the electrons around. It will still have London dispersion force, even though it's not going to have dipole-dipole interactions. So that's polarizability. It's really about, we've been using surface area as our shorthand for polarizability. There's other factors that go into polarizability that have to do with things beyond this class, like three-dimensional geometry, bond vibrations, external forces, linear, like there's a bunch of other things that go into it. For us in this class, surface area's polarizability is what we've been using to describe the main features of polarizability. Polarizability. Question?
I was just wondering if we need to know a lot about stationary and mobile phase of paper chromatography.
So the thing that you need to know about stationary and mobile phase is, stationary and mobile phase is just the thing that's sitting still and the thing that's moving. The important thing inside of the idea of stationary and mobile phase is what intermolecular forces are pulling the thing across the paper versus what are the intermolecular forces of it staying on the paper. And that's directly applicable to the gas chromatography as well, where there's a stationary and mobile phase. So that idea of the application of it is still important.
Okay, and the answer to that would be intermolecular forces?
Yeah, yes, there's more details to it than that, but yeah.
Simple
But
answer,
intermolecular forces is the direction of the answers. The intermolecular forces of the chemical compound with the water.
Adhesion to, I would assume, maybe? Maybe water forces, hydrogen bonding.
Well, yeah, so you'd be looking at water interacting with the chemical compound versus the chemical compound interacting with the paper, kind of looking at those two differences.
Gotcha.
So it's kind of like solubility in paper versus solubility in water and figuring out where it's more soluble.
Yeah.
If it's more soluble in paper, it stays on the paper. If it's more soluble in water, it travels.
Ah, I see.
And we saw the same thing with our gas chromatography in terms of when did the peak come out? Was it moving with the air or was it sticking inside the tube more? Right? Stationary phase was the tube. The mobile phase was the air blowing through the tube.
Wasn't that about boiling point too?
Yeah, so boiling point was part of what was pushing it through the tube and getting it to move off of the inside of the tube.
Sure.
You bet, see ya. Let's see, what time is it? 1:40. I've got a little bit of time to talk about the periodic table has a lot of information on it.
I was going to say, we don't have to talk about it if we don't
So some of the things that I think are useful, so if you're looking at your periodic table, right, you can talk about your n values, right, n equals 1, 2, 3, 4, recognizing that the D block lags behind 3, 4 when that one's 5, right, and then the P block will go back to the regular, so recognizing that delay is important. Recognizing you got your S block, your P block, your S block, your P block, and your D block. You can also put on your common charges labels. Right, this is your plus, +2. Not worrying about the halogens there. There's your -1 and your -2. Nitrogen can kind of do both. That's kind of, I don't like to put the +3 there because it's really just aluminum that does the +3 there. But those are our common charges. And you can put the periodic trends. I don't like just the arrows for the periodic trends, so I usually don't put those. See ya. Right, the thing that I like for the periodic trends is understanding them, but you can kind of generally say, like, this corner is high electronegativity, small radius. What else do we say about this corner? Those are the two important things, right? We could do electronegativity. We could also split it into high ionization energy, high electron affinity. But these two things, whoa, that's not how I want to draw that. These two things really feed into the electronegativity. So it's just those two that I really like to remember is the high electronegativity, small radius. Question?
For ones where it's like, if you're asking which of these atoms is going to have a higher electronegativity, and say it's something like, it's further to the right this way, but there's, like, say, like, you have, like, an S, but then you also have, like, C, which is higher up. So, like, how can you determine which one's more electronegative?
So electronegativity changes so dramatically from right to left because electronegativity depends on that electron affinity a lot, pulling electrons towards it. So it depends on how close it is to filling its valence shell. Like fluorine is significantly more electronegative than oxygen.
Yeah. Oxygen
is significantly more electronegative than nitrogen. Nitrogen is significantly more electronegative than carbon. Carbon's not very electronegative.
Yeah. Okay.
Right. So the steps across are really dramatic. So if you're looking at sulfur, sulfur with only 2 valence openings, that's going to be significantly more electronegative still, even though it's down a row.
Okay.
Now, if you went further, what's below sulfur?
Se.
Selenium. If you went to selenium, I'd be like, ooh, that's a little tricky, right? Because it's like much further down, a little bit further over. That one, I bet you selenium slightly more than carbon, but not much.
Okay.
And I would want to look at like number. That would be one of the ambiguous cases that I would not give you on a quiz.
Okay, gotcha. I
But
know
like-
that like NOF are gonna be like some of the highest.
The highest, right?
Okay,
And chlorine's pretty up there as well.
got it. Okay, so you probably won't do like a comparison between chlorine and one of those three, or NOF.
Yeah, you will.
So because if you're looking at chlorine to nitrogen, it's one step it's like a step down, but it's like two steps over, right? So it's like chlorine and fluorine, like chlorine is almost as electronegative as oxygen, actually.
Okay.
Because it's got that one more electron, so it really has that drive to pull electrons away from things.
Mhm.
So the right-left matters more than the up-down
Got it.
in the case of electronegativity, because of that valence shell filling idea.
Yeah.
Once you get over to nitrogen, the electronegativity starts to drop off like once you go from oxygen to nitrogen, the electronegativity starts to drop off really fast.
Okay.
Question?
I know that you put like the common charges, like hydrogen's plus, so that means the next row's +2, and then oxygen's 2 minus, so that means the next one's
One
minus
minus.
1.
Yeah.
But when we get like a molecule that isn't in that common area, how do we figure out what the charge is?
So if it's one of the transition metals, you kind of need to be told, right? And you're either going to be told in the compound, so I'll say like iron 3 chloride, or I'll say like magnesium 2 oxide, right? I'll say something about like the Roman numeral to tell you what the charge is on the metal, or it's going to be aluminum, which is always +3, right? And so boron is not always +3. Boron has some different oxidation states. Positive is often +3, but aluminum is kind of like always +3.
So then if it's not in those common areas and it's not aluminum, it'll usually tell you.
Usually, yeah.
Okay.
Yeah, you usually need some more information.
Okay.
So that's kind of, I mean, there's so much more I could say about the periodic table, but those are kind of like the main things that I think of.
Sure, that's fine.
Other questions? That kind of gets through the whole list. We've only got a little bit of time left in the office hours.
You also recommend just like memorizing most of the sheet, right?
Yeah, I don't like using the word memorize because if you try to rote memorize all of that, it's like a pretty big headache.
Yeah.
The polyatomic ions is the place where we need to put more of our time. Like all of the +1s, +2s, -1s, -2s,
Mm-hmm.
like all of those we can get from our periodic trends.
Yeah.
The polyatomic ions are ones that we need that are harder to get from the periodic trends, but we can look for, rather than trying to just memorize all of them, look for that kind of like broader organizing idea. Which ones are the which ones are the 8s, which ones are the ites, right? The way it begins, chlor, nit, phos, sulf, kind of tells you whether it's sulfur, phosphorus, chlorine, nitrogen. Like it tells you kind of what the other thing besides. All of them are oxygen containing, right?
Mm-hmm.
So you can use that hydroxide, right? Hydrogen and oxygen, right? There's hints inside of the names. The other thing to keep in mind is you don't get that sheet during the exam, but you get the equation sheet which has those ionic compounds list on it.
Yeah.
So you can use that. I would study those two things in conjunction with each other. So it's like, oh, I'm having trouble remembering the charges. Most of the charges are on the periodic table from the solubility list.
Yeah. Okay.
And so there's like not nearly as much to memorize as it seems. Like when you just look at that page and be like, I gotta memorize all of this,
Yeah.
it seems like a lot. But when you realize that like, oh, I've already got like the top third of the page
True. Yeah.
from periodic trends, and then like acids and bases we haven't quite gotten into deep yet, so there's probably not going to be a lot of that.
Okay.
And then it's just the polyatomic ions, and it's like, well, some of them are already given on the paper we are going to have,
Yeah.
and the names of them kind of suggest what should be in them.
Okay. Cool.
So like kind of looking for that those overarching kind of connective ideas, rather than doing the high school thing of making flashcards and just memorizing it all.
Yeah. All right. Sounds good.
Cool. But yeah, memorize them all.
in time.
Okay, I'm gonna go ahead and stop the video. I'll stick around and answer a couple other questions if there are such.